We present GLOVER++, unleashing the potential of affordance learning from human behaviors for robotic manipulation. The question we aim to explore in this work is, what do we expect the robot to learn from human behaviors? Previous paradigm of pre-training in human videos and fine-tuning the pre-trained model weights in the downstream task suffers from the implicit, unexplainable, and non-generalizable representations, which is not robust to scenario changes. In contrast, we adopt affordance learning as the training objective. The affordance representation embodies actionable human knowledge, reflecting the possibility of where and how to act. It is a kind of explicit, explainable, generalizable representation that can be learned from human demonstrations. To enable the large-scale affordance pre-training, we introduce HOVA 500K, a large-scale human object visual affordance dataset collected from human demonstrations. The HOVA 500K comprises 500,000 meticulously annotated images spanning 1,726 object categories and 675 action categories. The diversity of scenarios and views ensures broad coverage of real-world interaction contexts, while precise annotation of affordable points aligns better with robotic execution. Based on the HOVA 500K, we present GLOVER++, a global-to-local paradigm of affordance training policy. Specifically, the vision backbone and lava model are utilized to encode the visual and multimodal features, respectively. We define an affordance token AFF to encode combined visual and linguistic feature, which aggregates global semantic contexts. While the affordance representation is a kind of local representation that focus on point-level regions. Hence, the direct decoding leads to background noise. To refine the affordance representation, we cascade an extra local decoder, taking the output of global decoder as mask prompt. The background noise is eliminated effectively. And we can project the reason-precise affordance into 3D space for precise grasping. The global-to-local decoding mechanism balances global semantic perception and precise local affordance representation learning. We aim to unleash the potential of the affordance representation in diverse downstream tasks. Compared with Qwen 2.5 VL, a powerful VLM with strong spatial understanding, GLOVER++ provides more physically plausible and functionally grounded affordance predictions. By projecting affordance prediction into 3D space, GLOVER++ can perform zero-shot manipulation tasks in both the simulated and real-world environments. We show some qualitative demonstrations. The reasoned argmax affordance point from GLOVER++ is shown in the video. We also use affordance representation as an explicit knowledge prior for imitation learning tasks. RL-Bench is used for language-guided multitask imitation learning. We reason the affordance based on the language descriptions, and use the affordance to dynamically modulate attention weights of the original network. GLOVER++ improves RVT and RVT2 by +4.9% and +2.6%, respectively. Gains are particularly evident in tasks requiring precise control, for example, insert peg, stack cups. We also show that GLOVER++ has some extended capabilities, and the first is serving as a perceptual backbone for a high-level VLM planner. We show a demonstration. Qwen 2.5 VL split the task, put the jar into the top drawer into steps like open top drawer, pick up jar, move to top drawer, and invoking GLOVER++ for affordance grounding. It combines semantic planning and precise affordance prediction, and can be adapted to any VLM planners. Thanks to its spatial reasoning capabilities, GLOVER++ can interpret positional cues like left/right, top/bottom, to enable dual-arm affordance reasoning. For example, press the left and right buttons, and hold the left pot handle and pull the right oven handle. Thank you for watching.